Welcome to today's webinar on the Guide to Future Climate Projections for Water Management in Western Australia. Firstly, I would like to acknowledge that I am on Whadjuk Noongar Boodja and pay my respects to the Aboriginal culture that has existed for so many thousands of years, and that strong connection to country and the way that the caring for our land, waters and skies that has existed over the thousands of years. Water management is such an integral part of the way that we need to look after our land, water and skies, and it's very important to all of us, which is why we're here today. So acknowledging that I'm on Whadjuk Noongar Boodja, please feel free, anybody who's joining us now, to jump on the chat, acknowledge the country that you're from, say hi to friends and colleagues, as we have a great community of practice that we have here. So I would also like to acknowledge the new waterways partners. So they are the Department of Biodiversity, Conservation and Attraction, the Department of Planning, Land and Heritage, the Department of Water and Environmental Regulation, the Urban Development Institute of Western Australia, the West Australian Local Government Association and the Water Corporation. And as you know, all of these agencies work together to support new waterways. My name is Shelley Shepherd. I'm the Program Manager, and we work to build the capacity to deliver water-sensitive cities, integrated water management, water-sensitive urban design. So today is a webinar which is very exciting. It follows on from one that we hosted with Stormwater WA in December last year. And it was an awesome presentation by Nick Deeks, who spoke about the implications of AR&R climate change guidelines on WA stormwater networks. And the great thing is this is going to follow on from that presentation, and we are very, very lucky to have Scott Wills from the Department of Water and Environmental Regulation here today to talk to us about the guide that the Department of Water and Environmental Regulation has produced. So in a minute, I will put the link to the guide in the chat, as well as the link to the previous presentation, so that those of you who may have missed it or would like to watch it again can do that. So welcome, Scott. Thank you so much for agreeing to be our presenter today. So Scott Wills has over 25 years of experience as a water professional in Western Australia, with expertise in urban stormwater design, water-sensitive urban design, groundwater investigations and field monitoring techniques. Scott has recently completed a Master's in Environment and Climate Change at Curtin University and commenced work at the Department of Water and Environmental Regulation in 2023 as a Senior Climate Change and Water Specialist. And I would also like to acknowledge Scott as one of the early first champions of WSID. So Scott was integral in getting the learnings happening and building our community of practice, and has been part of this network for such a long time. So I'm very excited to have Scott present to us today. So welcome everybody. It's great that you've all joined us today. This will be recorded, and we will also have a Q&A session afterwards. So if you have a comment about just saying hi to people, pop that in the chat. But if you have a question for Scott, there is a Q&A function at the top of your screen. It would be great if you can pop your questions into that Q&A, and we will make sure that I can read them out to Scott at the end. Or at the end of the presentation, you might even be able to chuck your video on and say hi as well. So I'm going to hand over to Scott now, and yeah, go for it. Thank you, Scott.
Thank you, Shelley. Thank you for that generous introduction. And all your energy, hopefully I can carry that through this presentation on climate projections. So I would also like to acknowledge the country where I am, which is Whadjuk Noongar Boodja, and pay my respects to their elders. So I'm here to talk to you about a new guide that the department has developed with the Bureau of Meteorology and Water Corporation for how to choose and apply climate projections. This guide is an update to a guide on climate projections that we published in 2015. By the end of this presentation, I hope that you have a better understanding of climate science broadly, understand a bit more about climate projections and how they can be used for a risk-based assessment. And I hope you'll feel more comfortable dealing with the rapid evolution of climate science and its increasing complexity and uncertainty. The department has been tracking impacts of climate change on water resources, particularly those in the southwest, for a while now. In effect, we've been adapting to climate change for nearly 20 years in the form of our water allocation plans, drainage management plans, and water resource assessments. We're all familiar with the narrative around climate change impacts to water resources across southern WA. Up to 20% decline in rainfall, up to 80% less flow into dams than in the 1970s, and of course less recharge to groundwater. It was the very hot, very dry and very long summer in 2023-24 that has really driven home that southern WA is a global hotspot for climate change. We saw unprecedented impacts to the environment and water supplies in areas of the state that have never been affected before. So more than ever, the department is having to rapidly adapt the way that we assess and manage climate change impacts to our water systems and communicate those findings. Over the past 15 years or so, we've updated and refined the way we account for climate in water resource assessment and plans, leading to the guide that I'm going to go through with you today. I will be speaking for about 30 minutes, so there'll be plenty of time for questions at the end. This is the cover page for the guide that we published in 2015. It has served us well, but a fair bit has changed in the last 10 years, which has prompted the development of a new guide. Broadly, the changes have been the development of new generation of climate models. These models now produce analysis-ready time series data that we can use, and new methods have been developed for managing the uncertainty that comes with a changing climate. This is the new guide released in September last year. If you don't have a copy yet, the QR code in the bottom left will take you to the web page. I didn't write the guide, so I would like to acknowledge the authors, Jackie Scholf, Simone McCallum, Margot Turner and Artemis Kitsios from the Surface Hydrology and Hydroclimate branch of the department. I will also acknowledge the various climate scientists and climate experts from universities, the Bureau of Met and CSIRO, whose valuable input helped to make it a better document. This new guide presents contemporary methods for water management assessments using future climate projections. In an urban context, this guide is applicable to seasonal and annual climate analysis and continuous simulations for such things as water balance and water harvesting calculations, groundwater level assessments and irrigation schedules. It should not be used for flood risk analysis or stormwater system sizing because these assessments are addressed in Australian rainfall and runoff. Fundamentally, the uncertainty with these assessments is different, and I will discuss this further a little later in my presentation. To provide an outline of what I will cover in today's presentation, I will give a brief description of global climate models, and because I'm not a climate scientist, I'll try to explain this at a very high level, including how local scale projections are generated. Then I will talk about climate projections produced by BOM that are currently available for WA at a 5-kilometre resolution and which we recommend in the guide. These are the National Hydrological Projections, which I will refer to as NHPs. I will then spend a good chunk of time on climate uncertainty, which is really important because it determined why we chose the particular approach for the guide. I will discuss the differences to AR&R. Then I will run through the steps in the guide, providing some examples. Finally, I will talk about how you can access climate projection data. I apologise if I'm going over some information that you're already familiar with, but I think it's important that we all start from the same point. This slide summarises the information and projection data relevant for WA. The top line are the global climate projections that are delivered by the Coupled Model Intercomparison Project, or CMIT. The CMIT has different phases related to timing of release. So CMIT 3 informed the Intergovernmental Panel on Climate Change, IPCC, 4th Assessment Report, released in 2007. The department's first guide to climate projections, released in 2015, was based on CMIT 3 projections. You can see that it takes some time to create regional scale data from GCMs, and I will talk about this more in the next slide. CMIT 5 was released in 2014, and projections for Australia are available now. The Climate Change in Australia website is a great resource, and you can view information from 8 GCMs, decision trees, FAQs, technical reports. BOM started work on NHPs based on CMIT 5 in 2019 and released them in 2022. These are available now on the Australian Water Outlook webpage, and these are the projections that we currently recommend in the guide. CMIT-6 was released in 2022 and is the latest generation of models being used to develop new projections. The Climate Science Initiative, which is a program run by DWER, are busy working on new projections, collaborating with the New South Wales Government, Murdoch Uni, Pawsey Centre and others. Just a note that CMIT-7 is currently slated for 2029 and the release of AR7. The new guide is intended to be enduring, so while we recommend using the CMIT-5 data currently, it can be used with the new projections, CMIT-6, CMIT-7, etc., once they become available. So let's have a more detailed look at GCMs. GCMs are a computer-simulated mathematical representation of the Earth's climate system based on real data, where the Earth is divided into a 3-degree grid integrating the atmosphere, oceans, sea ice, topography, and land use, and simulating the interactions and feedbacks between these climate system components. By coupling these components, the models can better capture the complex and interconnected processes that drives the Earth's climate. Along the top of this slide is a simple process for downscaling future climate data for a hydrological assessment. One of the critical inputs to the models are future greenhouse gas emissions. There's been varying ways that these have been incorporated. CMIT-5 used representative concentration pathways, or RCPs, which are projections of greenhouse gas concentrations over time. CMIT-6 now uses SSPs, or shared socioeconomic pathways, which include a wider range of factors like population and GDP. The coarse resolution of GCMs from 100 to 250 kilometres really limits their ability to examine the impacts of climate change on local regions or towns. These plots for the southwest WA for land use and topography show this well. You can see the blocky resolution of these data in the GCM, and it's easy to see that these wouldn't be particularly useful for some climate impact assessments. So some method of downscaling and bias correction is needed. This corrects the differences between climate input and observation data and preserves important features in the projection data, like intra-annual rainfall extremes, for example. The climate projections can then be run through a hydrology or hydrogeological model or used in a simple analytical application for a local scale assessment. So how are the BOM's NHPs derived? This slide shows global to local modelling framework that sits behind the BOM's NHPs, which translates 4 global climate models into 32 local scale application-ready climate projections at a 5-kilometre grid scale. The NHPs incorporate 2 greenhouse gas levels or representative concentration pathways. RCP 4.5 is considered a moderate level, which may eventuate with modest interventions. RCP 8.5 is considered to be a worst-case emissions scenario with no interventions. 4 CMIT-5 GCMs were chosen from Climate Change in Australia's 8 models, as they best represent Australia's different climate regions. The 4 models selected also represent the full spread of projections provided by the 8 models. Global climate models were downscaled from 150-kilometre grid scale using a regional climate model, a technique known as dynamical downscaling, to the 50-kilometre scale. The downscaled climate data and the GCM data were then regridded to a 5-kilometre grid using 3 bias correction methods. From all of that, we get local scale climate parameters as daily time series data to 2100. Climate variables include precipitation, maximum temperature, minimum temperature, solar radiation, and wind speed. What makes the NHP dataset unique is the next step. Those climate variables were then run through the Bureau's National Landscape Hydrological Model, producing water balance variables such as rainfall runoff, soil moisture, and evapotranspiration projections. The end result is 32 projections in total, 16 for RCP 4.5 and 16 for RCP 8.5. These projections are summarised into maps on the AWA website. There are numerous other places that go for summary climate change information in the form of maps and summary tables, like the Climate Change in Australia website. But if you're undertaking some kind of water-related impact assessment or doing a planning exercise, time series projections data like the NHP is needed. Now we need to delve into the uncertainty in the future climate projections. There's uncertainty in future greenhouse gas emissions, uncertainty in physical processes in GCMs, in the downscaling of GCM data to the regional scale, and uncertainties in bias corrections. If we consider this uncertainty in the traditional way, this leads to the pyramid in the corner, which is referred to a cascade of uncertainty, and where the envelope of uncertainty increases at each level. Due to the uncertainty, there are potentially thousands of alternative future climates, so we can't create a complete sample set which will give us confidence to assess probabilities. What this means is we can't approach the projections from a probability perspective. This is a major shift from our old guide that prescribed a more conventional approach where we use statistics to describe wet, median, and dry futures. This gives the impression that we have a probabilistic review about what might happen in the future, which in fact we don't. To look at this another way, along the bottom of this slide is a nice graphic that shows the range in uncertainty, from a clear future on the left, level 1, to completely unknown on the right, level 5. Levels 2 and 3 are where traditional risk assessments are useful. Levels 4 and 5 are considered deep uncertainty. Level 4 is where the climate scientists tell us the climate projections sit. If you're looking for another source, this is how AR&R describes deep uncertainty. If you read book 1 fully, you will note that flood risk deals with different types of uncertainty than what I'm discussing here. So this new guide doesn't specifically address flood analysis, it defers to AR&R. The climate scientists tell us that because of deep uncertainty, rather than thinking about probabilities, we should be focusing on plausible future climates. Projections are a representation of some of the plausible future climates. I'll give you a moment to read this slide. So now we have a situation where we have many futures that are plausible. How do we make sense of that? All the BOMs NH32 NHPs are plausible, so how do you choose which projections to use? If your assessment includes modelling, it can be time-consuming if you want to run all 32 projections, and the result can be an overwhelming number of sometimes conflicting futures. Enter storylines, which is how we approach the uncertainty. Storylines is a method for addressing deep uncertainty that is gaining momentum in climate change risk assessment and communication. It's not something we invented. Storylines flip the old approach of first choosing a wet, median, and dry climate scenario and running an assessment. Instead, it's about developing a narrative that combines an expert understanding of the system and your known system stresses with specific characteristics of future climates. This way, we identify climate futures that are the most important to consider from a risk perspective or for making a particular decision, essentially making the climate change information decision useful. Instead of cutting lines through different projections using statistical analysis, we actually select individual model outputs to test the system. This approach captures the temporal variability, which is the cause of our biggest climate risks, and also explores the boundaries of plausibility, thereby guarding against false precision and surprise. For example, we might deliberately select a model that shows long droughts, one that shows an increase in extreme wet and dry, and one that shows a gradual decline in water availability, and then analyse all three to gauge an understanding about the range of risks. When considering future climate, we need to look beyond just changes to averages and consider the variability that stresses our systems, the severity and lengths of droughts, and time between filling events. The storyline approach can strengthen decision making by allowing you to work backwards from a particular vulnerability, risk, or decision point. At the bottom of the slide is a snippet from a recent journal article by Adam Sade, which highlights the benefits of storylines for selecting a subset of projections for analysis. I'll give you a moment to read it. So you can start to see what I'm talking about. As an example, this is what the 32 NHP future climate rainfall projections look like for a site in the Midwest. The storyline method is in selecting a subset of projections based on narratives around system knowledge and stresses, which for this example might lead you to the 6 projections highlighted here based on their climate characteristics. The reason we are picking individual projections to analyse rather than an ensemble mean or some other statistic that smooths the data is that we want to retain the temporal variability in the climate because it is the cause of some of the biggest climate risks. So to summarise the reason for storylines method in the new guide, to address adaptation challenges, we need to navigate a cascade of uncertainty in climate projections and connect to the decision space. Projections are not a prediction or a forecast. They are plausible representations of the future. The relevant question is not what will happen, but rather what is the impact of particular actions under an uncertain regional climate. The assessment is not a prediction or a forecast, it is an exploration of plausible futures and associated risks. We need to find language for describing the uncertainty and resist aggregation. By this we mean communicating the uncertainty, not being pressured into a single definitive statement. We need to explore storylines of climate impacts combining the best information from multiple lines of evidence. Linking to historical events in their proper context brings the salience to the risk which is well understood. This is an important note. Storylines are not just about future projections, but also about historical events. This is how you build knowledge of the system and stresses. Let's go back to AR&R briefly. Something that has come up in recent workshops is which climate scenario do you pick? This is exactly what we are addressing with storylines. Storylines will not assist with flood risk uncertainty, but it may be a useful approach for selection of timeframes and climate scenarios for analysis, because effectively you need to create narratives around the system stresses. The 4 SSP scenarios selected in Table 1.6.2 is most likely based on storylines because there are many more SSP scenarios to choose from, as we'll see in the next slide. Those 4 have been selected out of all these SSPs because they are most likely decision useful. So with all this background information, now we get to the new guide and the climate assessment framework. The framework guides users to develop storylines that help to identify which climate projections are relevant for making a decision, better embed risk in decision making, and provide useful context for communicating findings. The overarching principle of the guide is that climate change projections, whatever generation of climate models they are from, are all plausible and need to be adequately incorporated into water-related decision making. This is done by acknowledging those climate futures that are most relevant for assessing the climate risk to the water resource. The framework is broken down into a series of 7 steps. The light blue steps are about defining the context of the system and the decision and building your storyline projections to investigate impacts of plausible futures. Darker blue steps are about doing, the climate and risk assessment stage, probably involving some kind of numerical modelling. Here you're assessing potential future impacts. The green stage is about reporting and communicating the climate change futures, the associated risks and adaptation opportunities. We like to think that these steps are relatively intuitive and familiar for most planners. To work through these steps, we are strongly recommending that people do this with the right brains involved from the beginning: stakeholders, technical experts, traditional owner groups, ultimate decision makers. By including this input, we'll build a stronger representation of the system, get more insight into decision context, and ultimately be able to communicate your decision narratives more clearly. The first step is defining the context of your decision. Let's take a simple stormwater harvesting example. The context could be that the cost benefit for investment into an alternative water supply for irrigation in the southwest is only viable if annual supply is above some threshold volume, and you want to know how future climate might influence your decision to go ahead or not. Or a groundwater example might be that you need to assess a future maximum groundwater level for a development site in the Pilbara. There is a significant groundwater-dependent ecosystem nearby, which has cultural value as a freshwater spring. There might be other development occurring which will have a cumulative impact on the GDE. At this stage, you're also considering what time period your assessment needs to cover. This table is from the guide and gives an indication of the time periods from different applications, from between 10 and 30 years for allocation planning to longer time periods for drainage management and planning process. In this stage, you're also considering what adaptive management options are available to you. Maybe it's efficiency measures, maybe monitoring triggers and a response framework for contingencies. Once the broader context of the decision is defined, the next step is understanding the water resource. Here you might start by looking at historical data with your domain experts to identify vulnerabilities and thresholds you might want to analyse. Ultimately, you want to define the climate characteristics that drive the system and the system stresses. These will be climate variables and statistics, metrics, or indices. So for our stormwater harvesting example, we might be really interested in consecutive dry years. We know from a long-term monitoring this is a risk to water availability. Similarly, for groundwater systems, the long-term average rainfall isn't always what drives recharge, but rather can be within year rainfall above a certain rainfall event threshold that's needed for recharge. If we think about our groundwater example again, perhaps the groundwater is relatively shallow, but we're unable to install subsoil drainage. The aquifer is highly transmissive, and the GDE is a discharge point for the aquifer. Evaporation is an important climate interaction for the GDE, and you would be interested in maximum and minimum levels for the wetland. For the development site, the high groundwater flow means that the groundwater levels respond to high rainfall events. You may look at 90 percentile rainfall months in the future projections and compare them to projections with frequent high wet season rainfall totals. Understanding potential impacts and consequences is the next step. Again, this is where we recommend the domain experts are in the room, including traditional owners if it was appropriate, to understand the risk to water-based cultural values. Here you would do some pre-analysis of the climate projections using the climate metrics developed in the previous step. Using the example of the alternative stormwater supply in the southwestern WA, we know that frequent, very dry years are the greatest risk to water availability in the southwest. So from the projections, you could plot average annual aridity, which is the ratio of rainfall to evapotranspiration, against the occurrence of consecutive dry years, as we've done here. We call this a storyline plot, which can help us rank and choose subsets for analysis. It is also a useful visual tool to support our narrative. Clearly, you would want to model the possible futures that are higher annual aridity and a frequent occurrence of consecutive dry years, because that future would carry a higher risk. But we can also see that there are other possible futures that might have a more favourable outcome. For our groundwater example, the GDE complicates the analysis, so a groundwater model will be constructed. If the GDE appears to be flooded, you can evaporate more water on site or reuse stormwater rather than infiltrating it. It is at this step that if an assessment has been completed previously, you might want to consider how the assessment compares. You can create comparable metrics from earlier projections, plot them with the new ones, and see where they fall. By comparing key variables and metrics, you can consider if you need to update your earlier water management decision or not. If the projections and your level of risk are similar, you may be able to continue with what you've got without repeating the full modelling exercise. These next two steps are doing, and in many cases involve some kind of modelling. Here you use the knowledge of potential impacts developed from previous steps and your modelling results to assess the different range of impacts across a plausible range of futures and explore the resilience of the water resource to model climate futures. And if you have unacceptable outcomes, you look at those in the next step of treating climate impacts. Here you use the connections you have made between the climate change impacts and the water system to identify adaptation options and other levers that will reduce undesirable outcomes. In the storyline example of aridity and consecutive dry years resulting in different water supply volumes, this could mean finding other water sources, redesigning the supply, or developing water efficiency strategies to reduce demand for water and reduce the risk of not meeting the supply target. The plan, act, monitor, and evaluate cycle is a technique we already use in many applications to make adaptive changes to minimize risk as the future unfolds. So this includes alternative pathways or strategies to manage higher risk potential futures if they eventuate. This should include reviewing decisions and the level of risk as new climate projections become available. How we consistently and clearly communicate climate risk assessments is important for stakeholder understanding and acceptance of water decisions and adaptation options. Using the storylines you identified at the start provides you a useful context in which to describe the water resource assessment and modelling results. For the example about deciding whether to invest in alternative water supply, here is a storyline graphic from earlier with some modelling results showing where the target supply volume sits and across the climate projections, shown here by the black line. Using this approach helps to communicate the results that are an explanation of the plausible potential outcomes. In this example, some are very favourable, and the ones below the black line carry greater risk and impact. All of the projections are shown here, but maybe only 4 or 5 projections are needed to represent the risks identified. The focus on managing system-specific risks means that our decisions should be more robust and therefore planning objectives are more likely to be achieved because we've tightened the link with adaptive management. We hope that the framework will improve the communication between modelers, water managers, decision makers, and ultimately the end users of our decisions, especially working together for how we treat and adapt to climate change impacts. Missing something on the slide. You can access the Bureau projections online now and take a look at the maps and charts for areas you are interested through the Australian Water Outlook website. The NHP time series data is available through NHP Australia, and you can email the Hydroclimate team to assist with downloading this data. The Hydroclimate team is keen to hear your feedback on the guide and provides further support. There it is. So there's our email. Speaking of emails, you may like to sign up to the Climate Science Initiative mailing list. URL and QR code are on the screen now. And in case it's handy again, here's a QR code that takes you to the guide. So that's the end of this presentation. I hope you found this overview helpful and that you find the steps of the new guide intuitive, because we believe that they mimic the planning process which has been standard practice for a long time. Thank you very much.